useful matrix decomposition that Jose just talked about. And then, if there's time, I will talk about something that the book describes as a numerical miracle slash discrete convolution. So they are two different topics, but yeah, depending on the time, there might not be. We can talk about that. Okay, so the main takeaway of Jose's talk is that we can actually do this. Okay. This factorization is going to help us to do the runtime analysis, and yeah, and also in general to get a better idea of how we are defining things. I shouldn't have erased it. Never mind. So in general, when we have B1N, the way it looks is F n over 2, Fn over 2 conjugate, Fn over 2 conjugate. It's a block matrix. So in the boring case, one would just sit down and say, okay, if I want to multiply a matrix, a vector times this matrix, or just do the n over 2 n over 2 square operations I have to do and just wait for years to pass and let life go ahead. Or you can use this interesting factorization to continue seeing how this matrix looks like. So in particular, each of the blocks can be factored into the DBS form. I'm going to call it like that, so that it will look like this. D1 and over 2, D1 over 2, D1 over 2, D1 over 2, this one over 2, and this one over 2. Okay? So yeah, does anybody have questions about why we can do this? It's good. Okay, so these matrices, we will define them to be D2n over 2. This one will be B2n over 2. And the following one will be S2n over 2. Okay? So in general, what this sub-index stands for is the number of steps we are working in. And you will see why later. So in general, the way we define the DBS matrices looks similar. So BAN, it looks like B1 n over 2 to the n minus 1, 2 to the n minus 1 times. So it's like a diagonal block matrix. But note that note that each of these matrices is itself like a diagonal, like a block matrix, where you have the Fourier transform matrices. So this is n over 2 to the a, 2 to the a times, and each of these you can factor. So you can factor D1 n over 2 to the a. And the same for B and the same for S. Okay? So what I want you to notice is basically that these matrices are actually something we know. We know how to call. So can anybody tell me, like, how would you call, for example, this matrix over here? Okay. Well, this matrix, it has n over 2 to the a blocks, so it will be called dA plus 1n. This one will be called dA plus 1n, and this is SA45. So these matrices are going to be really useful to do the next step. Let me see what to write. Because we started with Fn equals d1n, d1n is 1n, right? But then we found out, oh, okay, we can factor this one over here into b2, d2, b2, s2. But then we could again see that this can be factored out using that observation over there. And again, we get something like d1, d2, d3, 3, s3, s2, s1. And so on we can go until we end up with something that looks like d1 up to dl, then dl, all these are n's, and then sl, n, up to s1. So L in here stands for the log of n, so we are assuming n equals 2 to the L. Why do we end up with this? Because the matrix in the middle, BL, it is a diagonal block matrix where each of the blocks is F2. And in particular, how does F2 look like? Can somebody tell me? So I think the rule of unity we are using here is w to the 2 pi over 2 pi I over 2, which is just minus 1. So basically we are having 111 w. This is 111 minus 1. Okay. So once we have this BL matrix, I don't think we can factor it furthermore because it would look just like the same matrix times the identity times the identity. So this is like the latest one that we can arrive to in our factorization. Even if it looks like things got complicated all the way down, they actually got faster, which we will just check right now. Yes. DAN, it will look like a bunch of block matrices, n over 2 to the n minus 1. And each of these matrices, it looks like I n over 2 to the a, I n over 2 to the a again, and then dn over 2 to the a, and then dn to the a. So I think this is how these matrices are defined, but also this is something to be careful about. These matrices are not the same as these matrices. These are the D matrices that we use in the factorization, but these are diagonal matrices. So note that multiplying times an identity matrix doesn't involve any significant multiplication. They are just zeros and ones. And this matrix, it is also just diagonal. So multiplying a vector times this matrix over here will just take n operations. Okay? So if we do this, we put a vector over here. We split it into 2. Multiplying by this one will just take n over 2 operations. Over here, we will just take this times this. This will take 0 significant operations, and this times this will take n over 2 significant operations. So all in all, multiplying by this block takes n operations, and multiplying times this block takes n operations. Wait, I might be wrong. Yeah, sorry. The length of this matrix is n over 2 to the n minus 1. So, sorry, I was sorry with this. So, the total number of operations that it takes to multiply a vector times this is n over 2 to the n minus 1. Okay? So can somebody tell me how many operations or how many significant multiplications it takes to multiply times this? So we have 2 to the n minus 1 times n over 2 to the n minus 1, which is just n. Okay? So each of the matrices here, it takes n operations to multiply times it. And similar happens to these matrices. This happens because note that SL is built of block matrices that are permutation matrices. I should write this down. Which one? Sure. So the second part is SAN, and it looks like S1 n to n over 2 to the n minus 1, 2 to the n minus 1, n over 2 to the n minus 1 times. Okay. So this block is a permutation matrix. This block is a permutation matrix, and all the blocks in the middle as well. So SAN is itself a permutation matrix. So how many operations do you think you have to do in order to multiply times this matrix? Just n, right? So this adds just n log n to our count. And we're just left with this matrix over here. But note that BLN was just a bunch of F2 matrices. So it looks like F2. The number of blocks we have here is n over 2. So multiplying anything by this, it just takes all of n operations, but in reality it's like n over 2 significant operations. Because each of the blocks F2 has just one like significant entry. So, okay. Right. Make it a little bit more visible. So summing up all of these number of multiplications we have to do, can somebody tell me what do we get? Rachel?
2 and log n plus over 2.
Which is exactly like what we want, right? So this is the running time of the Fast Fourier Transform with this algorithm. And it's actually really cool that we can decrease the number of operations we have to do in a regular mode or something to something that looks logarithmic, n times logarithmic, right? Let me see how much time we have. Okay. So I don't know, I leave it up to your decision. Do you want to talk about some kind of puzzle-like thing that they call numerical miracle or discrete convolution?
First one, miracle discrete convolution.
So what was your second one, discrete convolution?
Yeah, I want that numerical.
We should just vote. Who wants a numerical miracle? Who wants the discrete convolution? Okay, sorry. I think I should just go for it. Oh, yeah, wait a minute. Could I erase this? Yeah, remember we had a lot of matrices of this form, right? So this was part of the factorization of a Fast Fourier Transform matrix. But on the other hand, if we multiply times an adequate vector, this will be incredibly cheap. And the reason why this happens is because, so in this case, let's just take up to L minus 1. And then, yeah, let us consider the vector that looks like this. But then let us write it in base 2. And then, well, yeah, let's just write it in base 2. And in particular, in the case that n equals 8, how does this look? Okay, looks like this.
And that's a vector, right?
Yeah, this is a vector in C8. Okay, but then we're going to apply the matrices. Okay, in this case, 8 is 2 to the 3. So how many of these matrices are we going to use? From S1 to S2. So, yeah, okay. S18 is just the even odd matrix. But S28, it looks like S14 and S14. So it is a block matrix again. So first applying S18 is what we will do. So what we get after the first step is first the 4 even entries, right? So these 4. And then we get yeah, so we get basically 0, 2, 4, 6 and 1, 3, 5, 7. Okay? But then if we apply S28, can somebody tell me what we get? What's it?
0, 0, 0, 1, 0, 0.
Yeah, these two first.
0, 1, 0. 1, 1, 0. 0, 0, 1.
Aha.
1, 0, 1.
Mhm.
0, 1, 1.
Cool. So if we read from left to right like the entries of this matrix, it will be exactly the same as if we read right to left the entries of what we get.
Oh, damn.
Oh.
So yeah, that's it. Weird. Okay, I'm happy that you're glad about that. So there's not enough time for me to explain this. So I'll just, yeah, I think it doesn't even make sense to give an idea. Yeah, the main idea of the proof of why this happens is induction. So basically, just try to think about it. First, applying S1n, it just takes all of the even vectors to the first n vector, to the first entries, and then the last half of the entries, they are the vectors that that ending one, right? So look like all of the first entries they start in 0, and then all of the last entries they end in 1. And what you did was just shift them, and then applying the last matrices using how they are defined, like the recursive definition. Then you can see that they shift everything, all of these digits, right?
Oh.
So they will shift these digits. I should just write it. So they will shift everything over here, put it in the beginning, and then put the 0 in the end. So this is kind of bad explanation, but there's not enough time. And I think it's important to ask for questions.
So then the time is going to be reduced. So then
I think in the end it's still n log n, but it's something that we are very fortunate to see. still with the Fast Fourier Transform, it's n log n. So.
Yeah.
Does anybody have questions? Yeah.
So does this work for any V? Like, not just that particular V?
So
Probably not, right?
at least the way I proved it, it needed B to be exactly the numbers
yeah.
from 0 to n minus 1.
So then,
Yeah.
what do you do in the case that V's not that? It's like, okay.
What do you do? I don't
You
know.
just go to the-
Yeah, sorry. So, no more questions?